Hello, Physics 1 students, and welcome to your Prelab 7 lecture. Today we're going to be discussing friction. So here we can see a simple illustration of friction, and an important thing to know about friction is that it always opposes the motion. So in this case, this is our motion, right, where our acceleration is. So our friction is going to be 180 degrees from the direction of motion. So that means our direction of motion is the direction of F pole and the acceleration. So our frictional force, which is this guy over here, is going to be 180 degrees from that. So this is at 0 degrees, this is at 180 degrees. And you'll notice that it's F subscript K because it is a kinetic frictional force because our object is moving. We can see that here because there's an acceleration being produced. Okay? Now, last week we all but ignored our y-axis. This week we're going to actually care about it a little bit, in the sense that normal force is very important for calculating frictional force. But when you look over at the equation, it's still not going to really have an impact on our acceleration, at least in these problems. It's not. You will have elevator problems where that's going to be where the y-axis is going to play a major role. But that's just not the case with these horizontal motion problems. All right, so if we sum up our forces in the y direction, we have our normal force because I've defined up as positive, and we have our weight force, which we're subtracting because down is negative. And then we end up with, because we know Newton's second law, right? We have mass times our acceleration in the y direction, and we end up with an acceleration of 0, right? Because this is purely a horizontal acceleration. We have no vertical movement, no vertical component to our acceleration. So it doesn't matter what we have on the other side of the equal sign. We know that it has to end up being equal to 0, right? So we know that these are equal and opposite to one another. And of course, that is the case with horizontal surfaces where there is no vertical movement. The surface is feeling a certain weight force, and it responds in kind with its normal force. That's the reason that the object isn't flying up off the surface or plummeting down through the surface, right? Because that would be what vertical motion is. Now, where the action is taking place is in the x-plane. So if we sum up our forces in the x direction, we have F pull, that's this guy here, that's our positive one, right, because to the right is positive. And then we're subtracting our frictional force because that's in the negative direction. So we sum up our forces in the x direction, F pull minus Fk. This is equal to our mass times our acceleration in the x direction. And let's move that over so we can see it better. Okay? So again, like we had last week, you could have multiple masses connected to one another. For simplicity, since we're just introducing this, there's just one mass. But remember that this could be a system of masses. And actually, for all we know, this could just be the system view of several masses connected to one another. We really don't know. All right, so some terms for friction. So it seems to me that everybody has their own way of saying the same exact thing. So this is my way of saying the friction terms. So we have Fs max, and what that means is that's the force required to move a static object. So that force that it takes to just make a static object budge. That is what Fs max is. Fk, not surprisingly, the K stands for kinetic, right? So that means movement. So Fk is the force that must be overcome to keep an object moving. As I've said before, normal force, this is going to be capital F subscript capital N. When I write it, you could see it all kinds of different ways. Some people just do capital N, some people do lowercase n, some people do what I do. There are all kinds of ways of writing normal force. But when I write it, it'll be this way. Mu s, that's our coefficient of static friction. We'll get into that a little bit more on the next slide. And mu k is our kinetic coefficient of friction. Okay? So, important equations that you want to know for friction. These two guys right here. So Fs max is equal to mu s times the normal force, and Fk is equal to mu k times the normal force. Okay, So let's talk a little bit more about our coefficients of friction. So right here, we have an inequality showing us the relationship between mu s when the object is not moving, such that Fs is less than Fs max, okay? So in the inequality, you can see that we've simply rearranged the important equations from the previous slide. So this is our slide before with our important equations, right? So when you look at the equalities, you can see that we've just rearranged them, right? We could put the normal force back over on this side and get exactly the same equation, right? So what is a coefficient of friction? Well, a coefficient of friction is telling us how much two surfaces are sticking to one another, okay? So in the case of our static friction, when that's overcome and our object transitions from stationary to moving, that's telling us how much our object, our stationary object, is sticking to, let's say, our floor. So say you're moving furniture, how much our furniture, the legs of our furniture, is sticking to our floor surface, okay? Then if the object is moving, mu k, so our coefficient of kinetic friction, is telling us how much the legs of our furniture, our object, is sticking to our other surface, the floor. So mu s for, two given surfaces is typically going to be considerably bigger than mu k. And then of course, across different types of surfaces, you're going to have variations in what your coefficients of friction are, right? So I'm sure a lot of you have moved furniture before, and you'll have a heck of a time trying to get the furniture to move, right? So mu s is pretty big. Those surfaces are sticking to each other pretty hard. But then once you get the furniture moving, it's not as hard to keep it moving, right? So your mu k is a little bit less. The surfaces aren't sticking as much once they're already moving. Now, you might intuitively be able to glean that, hey, my mu k and my mu s would be smaller for my furniture legs on tile than they would be on carpet, for instance, right? Carpet would probably have a larger mu s with your furniture because they would be sticking to one another more. It's much harder. It takes a much greater force to move it. And that's exactly what's being said on the left side of the equation, right? So Fs max is that force that it takes to budge your furniture or your object, whatever it is, divided by your normal force. So this is the weight force that your surface is feeling. So your floor surface, what weight is that feeling? Okay? So if it's taking a much greater force to move it, well, then you're going to have a much greater mu s, right? Because the objects are sticking to one another more. And that's what the coefficient of friction is. It's a measurement of how much two surfaces stick to one another. Same thing holds true here when your object is moving. If your Fk, so if the force that it takes for you to keep moving that object is greater, then you're going to have a bigger mu k. If it's smaller, then your mu k is going to be smaller. That's because your surfaces aren't sticking to one another as much. All right, moving on. So let's take a look at a graph to illustrate what I was saying on the previous slide. So right here we have Fs, so this is where we were not moving at all, right? Then we have Fs max, so that's when that object first budges. And then we have our moving object here, okay? So essentially what I did to produce this graph is I had a block, some mass, right? There was a string connected to it. This string I connected to a force sensor, and then I pulled the force sensor, and then because the string was connected to the mass, that also pulled the mass. Okay, so that's what I did in order to get this graph here. So when we're stationary, obviously there's no acceleration. When we're moving, obviously there is an acceleration. So just like you're going to see in the lab video, you're in lab 7, you're going to be getting your Fs max value, and that's the value when you're pulling the block when the object first moves. And you can see that it peaks here, right? So it really takes a bigger force. You can see it graphically. It really takes a bigger force to get an object moving. But then, once it's moving, you can see that the force required to keep the object moving diminishes, right? So this, technically, if I could provide a constant acceleration, a constant force, this would be a completely flat line representing Fk, but I'm not perfect, so you can see there are little peaks and valleys here where the force that I'm pulling with is changing a little bit, okay? But I can tell you that this mass here isn't changing, so this is sort of a representation of Newton's second law again, right? So we can see that my force is changing, my mass is staying constant, the acceleration is changing with it, right? All right, so let's move on to a couple physics jokes. So why did the dead cat slide off the roof? Because it ran out of mu-s. Haha. All right, and then, don't tell friction jokes because I won't let them slide. Okay, Prelab 7 practice problems. All right, so they look like this, and let's move on to number 1. So we have a 1,200 kilogram car traveling along a horizontal road at a speed of 30 meters per second, about 65 miles an hour. It runs into an icy patch. The car skids to a stop. Assume the coefficient of kinetic friction between the tires and the ice is 0.1. So let's draw a picture and put in all the information that we were given. So we have a car. I didn't fill in that this is 1,200 kilograms, right? But it is down here. So here's our car. It is traveling at an initial speed of 30 meters per second. I assume this is a horizontal road, so that's why I've drawn it as such. So Vox is equal to 30 meters per second. We know that we have some frictional force, but we don't know what it is yet because we haven't calculated it. But we do know what our coefficient of kinetic friction is. They gave it to us. It's 0.1. We know that there's an acceleration, okay, because the car is slowing down. So we don't know what it is yet, but we will be calculating it. We do know the weight of the car, well, the mass of the car, right? So we can calculate the weight of it. So we know that it's 1,200 kilograms. So that means 1,200 kilograms times 9.8. That gives us the weight of the car, 11,760 newtons. Now, because once again, we only have a horizontal acceleration, this car is not moving anywhere in the vertical. They have not said anywhere in the problem that the car has left the roadway to go upwards or plummeted down through the pavement. So it's a safe assumption that we have no net vertical movement, so no net vertical acceleration, which means that our normal force is equal and opposite, which is great news, right? So if we sum up our forces in the y direction, we have our normal force. This is positive because I've defined upward as positive. And then we have our weight force, which we're subtracting because it's in the downward negative direction. And this is equal to 0, right? Because as we established, there's no vertical movement going on with the car. So these must sum to 0. So if we rearrange the equation, we can move our mg to this side of the equal sign. And we know that normal force and our weight force are equivalent, right? So that means our normal force is 11,760 newtons. Little side note here, since the car is slowing down and friction is opposing the motion, I defined the direction of motion, as I've mentioned many times before, as our positive direction. So just be aware of that. That is how I defined it. You may have defined it a different way, and that's okay. Just be careful with your signs. That's all. All right, so number 2. What is the magnitude of a kinetic friction force acting upon the car? Okay, so we're finding a kinetic friction force, so that's Fk, that's this guy right here. Well, we know our equation to find Fk, that's equal to mu k times the normal force. Well, we found the normal force, right? That's this guy here. So Fk is just our mu k times the normal force, right, which is this guy here. So 0.1 times 11,760 newtons. That gives us 1,176 newtons. All right, problem number 3. So what is the magnitude of the acceleration of the car? So it doesn't matter how you defined your positive and negative directions, if it matches mine, if it doesn't match mine, you are finding the magnitude, so you cannot possibly have a negative number. Whatever value you get for acceleration, you're going to take the absolute value of it because that's what magnitude means. Okay? All right, so as we established, there's no vertical component to the acceleration, so we know that the only net force is friction, and that is in the negative x direction as I have defined it. Okay, so when we sum up our forces in the x direction, we simply have negative Fk is equal to the mass of our car times the acceleration in the x direction, which is what we're trying to solve for. So we rearrange to solve for A. So Ax is equal to negative Fk over m, right? All we did was we divided both sides by m to get this. So Ax is equal to Fk, which is negative 1,176 newtons, as we calculated on the previous slide, right? And we're going to divide by 1,200 kilograms, which is our mass of our car, and we get negative 0.98 meters per second squared. Now remember, we want magnitude, so we want to take the absolute value of that. That means that the magnitude of our acceleration is a positive 0.98 meters per second squared. But if you defined your system the way that I did, you want to remember that there was that negative sign, because that's going to be important in the next couple problems. All right, so pre-lab practice problem number 4. How much time does it take the car to stop? Okay, so we're calculating t-stop here. So we want to recall from lab 2 that Vx of t is equal to Ax times t plus Vox. This is very similar to what we were doing in lab 2, except we're just rotating 90 degrees, right? Because we were working in the y, now we're working in the x. So remember, in lab 2 we threw up the beach ball, and up at the top of the motion we know that the velocity in the y direction was equal to 0. Well, now the car is going to stop in the horizontal, so that's in the x direction, so we want to know what time the car is stopping, t-stop. All right, so we set Vx of t equal to 0, and we know that it's at. So Ax, that was negative 0.98 times t-stop, that's what we're solving for, plus 30, that was what they gave us in the beginning as our initial velocity in the x direction. So there it is. All right, so we take our negative 0.98 t-stop, we bring it to the other side of the equal sign. Now it's a positive 0.98 t-stop, that's equal to 30, divide both sides by 0.98, and we get that t-stop is equal to 30.6 seconds. All right, pre-lab practice problem number 5. How far does the car go in that time? Okay, so we already calculated t-stop, so we know the time at which it stops. And if you haven't been in my class before, you may be wondering what's going on over here on the x-axis. How come there's t and x? Well, I typically will pair up my t and my x on the same axis, just so that I can include all my variables. So if you were confused by that, that's all that's happening here. I have my x and my t on the same axis. All right, so recall from lab 2, our position equation, x of t is equal to 1/2 ax times t squared plus Vox times t plus x naught. So we want to know the position of the car when it stops. I'm calling that x stop, so the position of the car when it stops, that's this guy here. So we have to plug t-stop into our x of t position equation. All right, so here we have x stop, that's equal to x of t-stop. That's equal to 1/2 ax times t-stop squared plus Vox times t-stop plus x naught. So when we plug in 30.6 for t-stop, because we calculated that, that's what it is, we get that x stop is equal to x of 30.6. This is equal to 1/2 times negative 0.98. Don't forget your negative sign, especially if you defined your coordinate system the same way I did. So negative 0.98 times 30.6 squared plus 30, remember that's our initial velocity, 30 times 30.6 plus 0, okay? And that's equal to 459 meters. So the car was skidding for a harrowing 459 meters. All right, pre-lab practice problem number 6. So in figure 4, M1 is equal to M2, and they're both equal to 300 grams. If the surface of the table is frictionless, what is the acceleration of the system? Okay, so I did include our internal forces, even though they don't contribute at all to our external forces, but here they are, just in case you wanted to see them. One thing that I want to mention, when I have a drawing, I never, ever, ever let grams make it into my drawing. Why? Because then your answer is going to be off by a couple orders of magnitude. Convert your grams to kilograms right away. Newtons are kilogram meters per second squared. Kilogram meters per second squared, not grams. Okay? So I would highly recommend when you're doing these problems and they give you the mass in grams, convert it to kilograms right away. Okay, enough of that. So we have mass 1, it's resting on a surface, right? So it's exerting its weight force onto the surface. Because it's not moving vertically, we know that the normal force, which is in response to the weight force that the surface feels, the surface is exerting this normal force that is equal and opposite to the weight force. Mass 1 is connected to mass 2 by a string that is run over our frictionless, massless pulley, because physics problems, and mass 2 is hanging down here, and this is also equal to 0.3 kilograms. Now, I think most of you would probably realize that an acceleration is taking place. This mass 2 is plummeting, and this mass 1 is moving to the right. So, since there's no friction in this case, M1 has no impact whatsoever on the net force of the system. I know that's pretty tough in the beginning to wrap your head around. When I was a student, I had a hard time understanding that too, but trust me, it has no impact. There is no friction. In the real world, there's always friction. That's why it's so hard, I think, to grasp, but there is no friction, so M1 has absolutely no effect on the net force. Wild, I know. Okay, so M1 is connected to M2. In here, there was a massless, frictionless pulley, but I've removed it for clarity because it's not really doing anything. I'm also going to remove these tension forces up here because they're also not doing anything, and this is a system of masses connected by a string. Okay, so the only thing that's really going on here is we have M2G, which is driving the movement of this system, and it's producing some acceleration, which is what we're interested in finding. So let's look at this as a system view. Since it is a system after all, these masses are connected inextricably by this string. So we have M1 plus M2 being influenced by the force M2G. Okay? So when we view our masses as a system above, we can see acceleration is only in the x direction, as I've drawn it. So we really don't care about the fact that the normal force and the weight force are balanced, as I said before, right? If we want to solve, if we want to solve for acceleration. If there was friction, then we would care, but there isn't, so we don't. So we're going to focus only on the net force in the x direction and solve for acceleration. All right, so sum up our forces in the x direction, literally just the one, M2G. That's equal to the total mass of the system, so M1 plus M2, times the acceleration, which is what we're looking for. Now we can go ahead and plug in the numerical values we were given. So M2, 0.3 kilograms, G, 9.8 meters per second, is equal to M1, 0.3 kilograms, plus M2, 0.3 kilograms, times our acceleration. So 0.3 times 9.8, that gives us 2.94 newtons. This is equal to 0.6 kilograms times the acceleration. Then, in order to get acceleration by itself, we're going to divide both sides by 0.6. So 2.94 divided by 0.6 gives us 4.9 meters per second squared. That is our acceleration. All right, problem number 7. It's a little bit of a doozy, but hang in there, we'll get through it together. All right, so we have the same figure, all right? Mass 1 and mass 2, once again, are 300 grams. If the surface of the table has a coefficient of friction, so now we have friction, and this coefficient of friction is 0.5, what is the acceleration of the system? All right, so I wrote down that mu k is equal to 0.5 up here. And once again, I have converted grams to kilograms right away, so I don't even let grams make it into my picture. So M1 is equal to 0.3 kilograms, M2 is also equal to 0.3 kilograms. Then I've also done some calculations. So normal force, I know that there's no vertical movement once again, so I know that the normal force and the weight force are balanced. So that means that the normal force is equal to M1G. That's equal to 2.94 newtons. Same thing with M1G, just in the opposite direction. Then M2G, exact same mass, same gravity, 2.94 newtons. The only thing that's different about this system is right here, our force of friction, okay, Fk. The reason it's Fk is because there's an acceleration. This block is sliding to the right. This mass, this hanging mass, is plummeting down, okay? So Fk, we know that's equal to mu k times the normal force. So we'll go through how we get to the system view once again. There is friction, so this is a little bit different, right? So mass 1's impact on the system's net force is Fk, right? Because when you calculate Fk, that equals mu k times the normal force, right? So this guy resting on the surface is the only thing that's creating this frictional force. This mass 1 dragging against the surface. That's it. This is once again a massless frictionless pulley. That's why I've removed it. They're connected by a string. The tension forces, they're going to go away because they have no influence on the external force. The only way that this problem is different is that there is friction, and that is Fk right here. And that friction is coming from mass 1 dragging against this surface, okay? And then the force that's making this system go and competing with our frictional force is once again M2G. So when we view this as a system, we have M1 plus M2. The force that's driving the motion is M2G. The force that's opposing the motion is the frictional force, as frictional forces are known to do. And so, once again, just like on the previous slide, the normal force and the weight force, M1G, are equal and opposite. And so we're able to set them equal to one another. So we found the normal force just like I was talking about up here. But here it is written out once again. So normal force is equal to M1G because we just rearranged this equation. We brought the M1G over here. So we know that it's equal to 0.3 kilograms times 9.8, right? M1 times G. That gives us 2.94 newtons. So now we can solve for Fk because we know the normal force and we were given mu k. So Fk is equal to mu k times the normal force, so 0.5 times 2.94, that gives us 1.47 newtons. Now finally, we can solve for what we're interested in, which is the acceleration. So we compute the net force on the system in the x direction, and then we're going to set it equal to the mass of the system times the unknown acceleration, aka Newton's second law in action. Okay, so here we go. Here's our net force in the x direction. We have m2g minus Fk. You can see up here in my system view, I have defined to the right as positive. Okay, so that's why m2g is positive. That's why Fk is negative. This is equal to m1 plus m2, so the total mass of the system times our acceleration. So once we plug in our values, we have m2 is 0.3 kilograms times g, 9.8 meters per second. Fk, which we computed up here, that's 1.47 newtons. this is equal to the total mass of the system. So m1, 0.3 kilograms, m2, 0.3 kilograms, times the acceleration. Down here, we've solved for what this is here. So 2.94 minus 1.47. Then we added 0.3 and 0.3. We got 0.6 kilograms times A. So when we difference 2.94 and 1.47, we get 1.47, right? Because it's just half of 2.94. And that's equal to 0.6 kilograms times the acceleration. Then in order to get A by itself, we have to divide both sides by 0.6. So 1.47 divided by 0.6, that gives us 2.45 meters per second squared. And that is our acceleration. And then over here, I just wanted to remind y'all to check your work. If you do two identical problems like we just did, and one has friction and one doesn't have friction, and absolutely everything else is the same, the frictionless acceleration better be greater than the one with the friction, okay? So you could see on the previous slide, right, we got 4.9. Here we got 2.45, so that totally checks out. But if that wasn't the case, that would be an indication that you would want to go back and just double check your work. All right, so I have some review. So as you know, the quizzes are 5 questions from the previous week and then 5 questions from the current week. So that means we're going to have some Atwood machine questions on the quiz and maybe a few others. So let's just review Newton's second law, because we talked about that a lot last week. So Newton's second law, if we have friction, it would look like this, right? We have some mass being pulled, friction's opposing the motion. It's on a horizontal surface, so we have the normal force, which is responding to the weight force, but these are equal and opposite, so they cancel out, and we just have a horizontal acceleration. So if we sum up our forces in the y direction, we get 0 newtons, right? Because normal force and weight force are equal and opposite. There is no net acceleration in the vertical, so that's how we know it's equal to 0, only horizontal acceleration. Then where the action is taking place in the x-plane, we have F pull, which as I've defined the directions, that's our positive direction, minus Fk. So if the acceleration and the object are accelerating to the right under a purely horizontal pulling force, when we apply Newton's law, that means that F pull minus Fk is equal to our mass times our acceleration, well, I guess technically in the x direction, right? So there we go. Perfect. So now if we had the same situation without friction, let's say we have a 10 kilogram mass being pulled by a force of 20 newtons along the positive x-axis across a horizontal frictionless surface, what is the acceleration of the mass? Okay, so now we have no frictional force and we have some numerical values. So if we sum up the forces in the y direction, once again, they're equal and opposite one another. Okay, so they cancel out. We have no net acceleration in the vertical. Once again, only horizontal acceleration. So we're trying to find the acceleration. We're dealing with the horizontal. So Fx is equal to F pull, right? Because there's no friction. So that's it. That's all that's going on in the x direction. F pull. And this is equal to our mass times our acceleration. Now remember, if we had multiple masses together, this would be all of our masses. And for all we know, 10 kilograms could be a whole system of masses, and we're just viewing it as a system, right? So, moving on, we know that F pull is 20 newtons, we know that our mass is 10 kilograms, and we're trying to solve for AX. So, 20 divided by 10, that gives us 2, so our acceleration in the horizontal would be 2 meters per second squared. All right. Reviewing Atwood's machine. So say we have 2 objects connected by the string and the string is run over a pulley, making both masses suspended vertically. If m1 equals 1 kilogram and m2 equals 2 kilograms, what would the acceleration of the system be? Okay, so this is exactly what we did last week. I'm just doing it again so that it's fresh in your mind for the quiz. So we have our free body diagram, all forces drawn exactly as it's been described, right? So just like last week, we have M1, we have our tension force up, we have M1G down, we have our pulley, The string is run over the pulley connected to M2. We have the tension force up and the weight force down. Now we know that mass 2 is 2 kilograms, so this guy is plummeting. This guy is only 1 kilogram, so he's flying up, right? So over here, I'm drawing my acceleration downward, okay, in the direction of M2G, because that's what's happening, right? This is plummeting downward. So if we view our mass system depicted horizontally, removing our pulley, our massless, frictionless pulley that's doing nothing really, then we end up with this, right? So massless, frictionless pulley was here, now it's gone because it's not doing anything, but our masses are still connected. That makes them a system of masses, right? So we should be viewing them as a system down here. So we have M1 plus M2, and then to the right we have M2G, that's what's making the system go, and then M1G is opposing that motion, right? But not strongly enough to stop it because there's an acceleration, right? So the acceleration is in this direction, so I'm defining the direction of the motion as the positive direction. So we sum up our forces in the x direction. We have M2G minus M1G is equal to M1 plus M2 times the acceleration, right? So Newton's second law in practice. So we're going to start plugging in our values. So we have M2, 2 kilograms, G, 9.8 meters per second, minus M1, 1 kilogram, times gravity, 9.8 meters per second, is equal to M1, 1 kilogram, plus M2, 2 kilograms, times the acceleration, which is what we're trying to solve. So when we multiply this out, we get 19.6. When we multiply this out, we get 9.8. This is equal to 3 kilograms, so 1 plus 2 is 3, times the acceleration. Now we want to get acceleration by itself, so we need to divide both sides by 3 kilograms, and we get 3.27 meters per second squared. That's our acceleration. So one thing that I wanted to mention is, just to make sure that y'all are understanding, what force would we have to apply to the system to stop the motion from taking place? Well, we would have to apply M2G in this direction, right? If we applied M2G in this direction, because that's what's making the system go. If we subtracted M2G from it, then this would be 0, just like we typically have in the y direction, right? So then if the net force was 0, we would have an acceleration of 0. So that would be it, right? That would stop the motion. Okay. Okay, so another thing that I wanted to mention, just because it seems to me that a lot of students are kind of on different pages when it comes to dividing fractions, so I just want to make sure that everybody is on the same page, okay? So if you have a fraction a over b divided by another fraction c over d, I think we would all agree that a over b divided by c over d is exactly the same as this, right? One thing that I've noticed that students aren't aware of all the time is that a over b times the inverse of c over d, so d over c, is also the same thing. So you could get AD over BC, and that's a simplified version of this big monstrosity over here. So in terms of numbers, if you had 1/10 divided by 1/5, that's 1/10 divided by 1/5, that's equal to 1/10 times 5 over 1. So 5/10, and then we know to simplify our fractions, right? Reduce them, and we would have 1/2. Then say you have 3/4 over 10. I think we would be comfortable saying that that's the same as 3/4 divided by 10 over 1, because 10 over 1 is 10. Any number divided by 1 is itself, right? So we could also say that this is equal to 3 over 4, so 3/4, times the inverse of 10 over 1, so 1/10, and then we would get 3/40. And you can do this on your calculator and check this too, if you don't believe me. And then if we had the reverse scenario, so say we have an integer in the numerator and then a fraction in the denominator, so 8 over 1/2, that's the same as 8 over 1 divided by 1/2, which is the same as 8 over 1 times the inverse of 1/2, which is 2 over 1, so then we would get 16. Now, in terms of graphing, right? This is our y-axis, right? This is our x-axis. So if we want to know what the slope is, we want to take our fraction from the y-axis and divide it by our fraction from the x-axis, right? Because slope is our change in y over our change in x, our rise over our run, right? So that would look like this. So u over ri divided by GHT over r. So if we write that out, we have u over ri is divided by GHT over r, which is the same thing as u over ri times the inverse of GHT over r, which would be r over GHT. And you can see that if you did this correctly, you would find that you're right. And that's a good thing. All right, units and slope. So let's do a couple of practices here where we're practicing dividing our rise over our run. So if we have acceleration on the y-axis, and we have 1 over our mass on the x-axis, that would be a over 1 over m, right? Or we could say it's a over 1 divided by 1 over m, which is the same thing as a over 1 times m over 1, right? So am or ma. So the slope of this would be force, okay? Over here, we have force over acceleration. And I think that one's pretty simple for us to rearrange, right? We know that force is equal to mass times acceleration, so force over acceleration is equal to mass. That means the slope of this line would be giving us the mass. And then this one isn't as closely related to what we've done already or what we're doing today, but just another good example. If we had mass divided by volume, especially because we're going to be doing our buoyancy lab next week. If we have mass divided by volume, we would know that the slope of this line is density. And one last thing, a little bit unrelated, but I'm hoping it's helpful for your report writing. If you don't know this shortcut, I've found it extremely helpful over the years, so I just thought I'd pass it along to y'all. So if you hold your control key and the plus equal sign together for a fraction of a second, this is a shortcut in Word and PowerPoint, not Excel, unfortunately, sorry, to get subscript. So basically, if I were to be writing, H2O, right, and I wanted to make this a subscript, I go and I highlight it, and I do Control, plus, and there we go. Now I have a subscript, okay? All right. Then if I wanted to get my superscript, I would hold Control, Shift, and the plus / equals key, and that would be a shortcut in Word and PowerPoint, not Excel. Once again, unfortunately, I wish they would update it so they all did it. But this is how you get superscript. So say I had meters per second squared, right? And I want this to be a superscript. There we go. Now it's a superscript. Don't even have to open up the whole font dialog box thing and go in here and change it to superscript, right? There's a nice shortcut for that. All right, so hopefully that helps, and hopefully you did find all the pre-lab practice problems helpful, and best of luck on quiz 7.